Welcome to Ambiq's ongoing AI learning series. My name is Carlos Morales. I run the AI team at Ambiq. And today I'm going to talk a little bit about some AI-specific optimization techniques that I've kind of developed when working with Ambiq devices. Some of this can be generalized to other platforms, but really we're going to get specific here to Ambiq Apollo devices. Today I want to talk about three things. One is kind of a refresher on how inference is computed. It's important to know when you're optimizing, what is it that you're optimizing? What is it that you're computing? So I'll talk a little bit about that. And then I'll talk about some of the obvious knobs I tweak when I'm optimizing for power, which is really what we're talking about here today. And then some obscure knobs that I've run into, and I do mean obscure, things that shouldn't make a performance impact, but do. And then I'll wrap it up talking about some of the features that neuralSPOT offers that help you with this process. Before I get into it, this is a general optimization problem, right? There are some specific AI things that I'll get into that make it a little bit more difficult, but in general, we're just optimizing. We're optimizing for embedded devices. And my number one rule for optimization is you optimize where the power is being spent. So today we'll talk about inference, but keep in mind that the bulk of your power is not being spent on inference, a very small percentage of it. So here's a typical kind of waveform, power utilization waveform, where we're capturing data over about 6 seconds. And the reason you're seeing different kind of utilization numbers across those 6 seconds is because part of it, we're not doing anything, and there's a voice activity detection model running. And then right around the middle of those 6 seconds, I start talking, and it goes, okay, voice detected. I can stop that model, record some time, and then we do a speech-to-intent inference. And that's 76 milliseconds. So out of your 6 seconds, what we're talking about today is optimizing just those 76 milliseconds. It's important to optimize that, and it's good to know how to do that, especially for folks in the AI development space. But remember that this is really an end-to-end problem, and to get to that really small power envelope, you need to optimize across the entire application. So here's a quick refresher. This is an old slide. I'm just kind of pulling it up again. Just to talk about how inference works, right? So inference, you have an input. In this case, it's an image of my poor dog in a Santa suit. And you feed it to a model that's going to infer what that picture is about. And typically, models are arranged in layers of neurons. So those little bubbles are neurons. The connections are synapses. They're not really, but and then each one of those vertical things is a layer. The important thing here is that there's two kinds of data that are being moved around. One is that are being operated on. One is a static set of data, which are the weights of the model, and then there's a dynamic set of data, which is the activation, how those weights activate the synapses as the data is fed and then produces an output. And so you optimize each of those things slightly differently, of course. Now, this is a toy diagram. Let's talk about what a real model looks like. Okay, so this is the model architecture of a very simple model, the speech-to-intent model that we started working from. And this is not our latest one, which has kind of a recursive neural networks and everything in there. This is a simple one that's basically just composed of a bunch of 2D convolutions. And so on the left-hand side, you'll see the entire model. And you see it's quite a number of layers. And this is a simple one. Big models get into the hundreds, if not thousands of layers. And we can actually run some of those in our embedded devices. So this one is not necessarily a stressful model from a weight size point of view. Another thing that you'll note if you squint is that there's a pattern. So models are AI developers are lazy, right? They'll take a pattern and kind of cut and paste it. You'll repeat it a number of times, and that's pretty typical. It's not because we're lazy. It's because we're trying to emulate and we're trying to get to um to a desired result that mimics the brain in some way. And brains have these hierarchical systems as well. So you'll squint and you'll see that there's a pattern here and then it repeats and repeats. So there's four kind of layers of convolution, depth-wise convolution, max pooling. Each one of those boxes corresponds to that vertical set of neurons that we talked about. And so the reason I pull this up and then I kind of blow it up, so this is the beginning of that diagram, is that the way that you compute is you take an input, and in this case, the initial input is a 100 by 13 um, feature, input tensor, and it's not a dog. In this case, it's a spectrogram. Uh, and then you feed it to a layer, and the layer will do some compute on it and spit out another result, and so on and so forth. Um, and so that repeats layer by layer until you produce a result. In larger, like in accelerator models and things that run on GPUs or dedicated AI accelerators in the cloud, the entire model will kind of fit on the accelerator. And there's a lot of work that goes into you actually bring the compute to where the data is. And that's very efficient. And you need that to, because you're spending acres of compute on a problem like Dolly, you need to be efficient. On a CPU, it's slightly different. And CPU, especially a constrained CPU like a Cortex M4 with just a little bit of RAM, what you're doing is you're kind of slicing through your weights and you're feeding that data into each one of those weights, and then you're operating on that. Sorry, you're feeding that data into each one of the layers and you're operating on that. And so what that looks like in the case of TensorFlow Lite for microcontrollers is there's an interpreter that's looking at the model weights or the model architecture, which has associated weights. It decides, okay, that looks like a conv2D. It takes that, it does a bunch of computation on that input, a lot of computation. Sometimes it has to transform it into a different shape. At the very least, it's copying and pasting it from a buffer to another buffer. It feeds it to another wrapper, which is kind of the convolution wrapper, and there's some optimizations that happen there. If you look at the code, you'll see that certain shapes, if it's an 8 by 8 convolution, it does something. If it's a 16 by 8, it does something else. So there's some optimization that happens there, but it's more wrapping code. And then finally, at the bottom, at the kernel, the thing that actually does the compute, that does a for loop inside for loop inside for loop, that computes this, we usually invoke ARM's CMSIS neural network library. And that's what you're seeing there in the actual code. And the reason I cut and paste that there is that you see that there's a lot of inputs even to that, right? So you're telling this you have to compute all those inputs, right? You have to kind of put them in the right shape. And you're telling CMSIS what the input dimensions are, what the input actually is, what the filter dimensions are. And when you're talking about a convolution, there's these filters. You talk about the quantization details, bias details, and then you have to talk about the output. And then CMSIS does some magic inside it, and you have to kind of trust that it's doing the optimal compute for what you gave it, and it'll produce a result. So there's not much I would say that we do around the CMSIS stuff. But in terms of what you do before the interpretation wrappers and so on, getting things to the right shape, that's where you can make the biggest impact if you're using TensorFlow Lite. Okay, and so this is a good time to pause and talk about the different ways that this kind of compute can happen, right? So the top things are kind of common, right? We use a framework to specify a model. Frameworks can be PyTorch or TensorFlow. Those are the big ones. There's other frameworks. That framework will compile it into a list of operations that you saw. So that diagram is from an application called Netron. The input to that diagram that you saw earlier is basically a computed, a defined model architecture. And so that's basically what is the output maybe of that operations graph or the graph lowering stuff. And then if you're going to run it on an embedded system, you have to optimize it and turn it into something that your runtime can run. So the thing that's actually running on your Apollo 4 is down here, right? It's either an binary that's compiled from that operation graph, or is an interpreter that's going to walk through that operation graph one layer by layer and compute per layer. And so the state of the art right now is that the head of time compilers are really not optimized for embedded systems. But there's a company called OctoML that is finally focusing on making something that runs on embedded devices. And the third alternative for ahead of time is you do it by hand. And so today we have in the audience Paul Chen, who's actually writing. He trained a model in TensorFlow, took the output of that model, and he has handwritten code that invokes CMSIS and then underneath it. So that's written in C, so you can use GCC. The beauty of that is that, GCC is the product of thousands of hours, thousands of person years, of development. So if you're going to compile something for a CPU, it's probably the optimal way to do so. So those are all cool, but what we're going to talk about is the left hand, which is TensorFlow Lite for microcontrollers, which is an interpreter, and how I've gone about optimizing that. TensorFlow Lite for microcontrollers, TFLM, I always do that, is kind of the golden gateway to embedded devices. And the reason for that is it's just simple to use. You take a model, you don't have to do a lot to it. You export it to your, a header file, and you can execute that. So a lot of the NPU vendors and the other accelerator vendors use that as a front end. And so it gets pretty complicated. Here I have like if you're trying to run something on a N55 or a Cortex M4, you will take the middle path, right? If you happen to have a U55 which is a NPU from ARM, then you use a compiler which looks at your model and says, okay, this is the optimal way to kind of lay out your model using our hardware. And every NPU vendor has something similar to that. So it gets complicated, I guess is the point I was trying to make. All right. So let's talk about TFLM a little bit. Right? I have problems with it. It's easy to use. In fact, if you want to get something running quickly, it's one of the only ways to get it running quickly, and it's very portable. So if someone's already developed their model on something on X and they want to run it on an Apollo 4, there's not a lot of work that you have to do. You just have to kind of change how you do the inputs and outputs, and everything else works. But it's really difficult to optimize. And there's three reasons for that. One, it's an interpreter. It's not compiled code. So, a fine optimization, loop unrolling, in-place compute, all that stuff that you get for free if you're compiling something in Clang or in any GCC Clang-based compiler or GCC, you're not getting that. The interpreter is very optimal, but the operations that the interpreter is executing are not optimal. And because you don't know what you're going to be running, you can't optimize a priori. You can't optimize before you run it. In fact, TensorFlow Lite for microcontrollers can't even tell you how much RAM it's going to use before you use it. Right? So it's crazy. You load it up, you cross your fingers, you kind of allocate some RAM to it, and then it tells you whether it worked or not. Right? And there is a way to print out how much RAM it actually used, and then you tune it back. But that's the kind of problem that you run into with an interpreter. The second problem is it's brittle. And what I mean by brittle is as long as you stay on the well-worn path, it'll kind of work, and it'll work fairly quickly and perform. But if you change anything, your performance can drop off 100x if you're using a non-optimized kernel or whatever. And because it's an interpreter, and it's a really it's a thicket of third-party packages piled on third-party packages, and there's all this kind of stuff. Unless you are basically one of the TensorFlow developers, it's going to be hard for you to root cause what caused that problem. Here's a great example. I just talked about figuring out how much memory you use. So the way you do that is you call a function inside TensorFlow called get arena used bytes. And I was printing that out in one of my benchmarks. And then when I cleaned up the benchmark to upload it, I deleted all my prints because that's what you do, right? You get rid of all your debug prints. My performance dropped 10%. That print or that invoking that function should not have an impact on performance. It's going and fetching some data structures and computing something, but it had a 10% impact. And when of course, I spent a day kind of bisecting my code, seeing where I lost my 10%, my 20 microjoules. So that I call that brittle. I call that small impact. The small changes have unpredictable impacts. And then it's not broad. So TensorFlow Lite, the TensorFlow itself has almost 1,000 different kinds of operations. Each one of those layers is an op. And because TensorFlow is designed to be broad, be able to compute almost anything, it has 1,000. But TensorFlow Lite for microcontrollers has a couple of dozen. So you can't just take a model from the real world and hope that it works, right? You probably have to re-architect your model. That being said, it's basically the industry's go-to standard. It is, to paraphrase Winston Churchill, it's the worst embedded system apart from all the others. Okay, so let's get into tuning. Big knobs or maybe obvious knobs are, how you place your memory. I remember there's different kinds of memory that you use. Clock speed. So it's not obvious. Usually we think slower clock is going to be more efficient, and it is, but it's not as efficient as you think. And I'll get into why that is the case. Turning stuff off, that in our world, that's of course obvious. And then in-place processing, copying and pasting buffers is very bad. Okay, and then the less obvious knobs are TensorFlow Lite version. It evolves almost weekly. How you link these libraries in, this should have no impact, but it does. And then compiler settings, data alignment, so on. And I'll get into the details. And then what I won't get into is the sledgehammer, which is just get rid of TensorFlow, write it in C as Paul is doing, and then you can optimize that as you would any other application. Okay, so let's get into the obvious knobs, right? So memory placement, we have a lot of choices in our world. We can put, remember, we have two things, right? Weights and, well, actually we have three. Weights, the activations, which is the tensor arena, and code. I have so far played with weights and tensor arena, and I can say that if you can get the model into TCM, do it. These models are usually 100 to 300K. So depending on how often you're going to be calling it, maybe you want to copy it into the tensor arena for a little bit. Sorry, into your TCM and then get rid of it. Or you might want to leave it where it is. But the cost of leaving it in RAM is about 2%. So it's a small impact, but it's something that you have available. The tensor arena has to go in RAM. So if you can put it in TCM, there is a bigger impact for shared SRAM. Our shared SRAM latencies are higher. So this one, again, you can copy it into TCM, operate, and send it back out if you're not going to be doing that too often. Tensor arenas are 25 to 100K, depending on the model. That's the optimal size. Sometimes we have bigger activation spaces. And then code. And so code is something that, because it's a little more involved in how you do, mostly it's JLink, trying to get code into RAM. And then the linker, putting all the addresses in the right place. I'm still working on that. So I can't tell you how much impact it will have, but it stands to reason that executing out of most of these, the interpreter will fit in an instruction cache. So this is why I can't really predict whether this is going to work or not. You can also play with clock speed, and here is a little counterintuitive. So Apollo 4 Plus has really easy, almost frictionless, changing of clock speeds. I can, without very much energy cost, I can flip to a lower or higher clock speed. So you assume that switching cost goes to zero. And so maybe you execute most of your code in like 96 megahertz. And then when you do your interpretation, your inference, maybe you go up to the full speed. Staying in low speed will save you about 5x, but it will double, of course, your computation time. So it really depends. Remember, that's only 76 milliseconds. So how much are you gonna, how much latency are you willing to spend to get that 5% over that 76 milliseconds? It really is application dependent. Turn stuff off. We have a lot of peripherals that you can turn off if you're not using the IOMs, the UARTs, crypto, and so on. We have memory banks. So if you're only using, say, less than 128 of your K of your TCM, turn off the rest. And there's a bunch of other features that you can turn on and off. And then something else that's kind of hard to do, but has big impacts, varying impacts, is in-place processing. So, the naive way is of operating on your incoming data is you have, your audio ADC or something will DMA your data in to a chunk of RAM. You will copy it somewhere else. You will compute your spectrograms, which will copy into somewhere else. You copy that into an input tensor. You operate the output tensor. You copy out. So those copies, they're pretty efficient, but they consume various amounts of processing time and energy. So if you have a library that can operate in place with minimal memory copies, that's better. It's hard to do, but it's definitely beneficial. All right, and these are some of the obscure knobs, and they're top of mind because we just went through an optimization exercise. So which version of TensorFlow Lite for microcontrollers you use to interpret has an impact? And the non-obvious, the obscure bit, is that you would think that as the versions go up, as you get more and more recent versions, your performance goes up. And in terms of pure performance, it does. So, a version from a year ago might be 1 or 2 milliseconds slower computing the same operation. But what happens is the energy goes up too. So the energy per inference goes up. So if you're optimizing for energy, which is what we tend to do at Ambiq, it's not obvious that you always want to use the latest. Here, you really have to experiment, and it really depends on your model and your application. The linking order has a lot to do with it too. So whether you link your standard library before a TensorFlow Lite for microcontroller library or after has uh, it has a performance impact, 2%. 2% makes a big difference when you're optimizing, but it's not always the same, right? So depending on your TensorFlow Lite version and your architecture, you have to play with both and see which one is better. Um, the Dash 03 is the maximum level of optimization for GCC. I find that saves about 2%, but it increases TensorFlow Lite for microcontrollers library by about 10% of memory size and binary size as well. So if you can trade off some MRAM for that 2% that's available to you. Otherwise, optimize for size, you will lose that 2%, but it's a very application specific optimization. And then so the weights and the activations, we align them normally to 16-byte 16-byte boundaries. But inside the weights, they're not always aligned. So the TensorFlow Lite for microcontrollers uses something called flat buffers inside it. They're not, it's not super sophisticated how they align. But we have a script that will read that into memory, copy it somewhere where the compiler forces the alignment, and then copies it back into padding, a padded version of that. So your weights go up by a few bytes, not a lot, but you can save up to another percent. Not always. Right? Sometimes I see 0%, and so I called it 0.1. Up to 1% is the most I've seen. Now, I just threw a lot of knobs at you, right? And the problem is they're not deterministic. There's no one set of configuration. There's no one optimal configuration that works for every model, every application. And so you have to experiment. And to run an experiment efficiently, you really need a way to set up the experiment in a way that doesn't involve a lot of coding, right? So a good kind of framework for experimenting. And then you need a way to measure the impact of that experiment. And in our world, we use an energy monitor like a joule scope or something similar. And so how do you talk to the joule scope to make sure that you're marking the important parts of the measurement? And so let's talk a little bit about neuralSPOT, which is our internally developed uh, Ambiq-specific AI SDK. Right. So first, let's talk about the block diagram here a little bit. neuralSPOT is all the blue stuff. There's some tools, scripts, and so on that help you do some of the stuff that I just talked about. We have examples that uh, show how we've done optimization for different kinds of uh, uh, models and applications. And so you can use those as a reference. And then we have an SDK that lets you do all kinds of power optimization and so on. And so that's in general, that's for all of AI. For power specifically, for power optimization, which is what we're talking about today, there's a power settings library. So the power settings library is an easy way for you to it abstracts Apollo 4 Plus's many power setting knobs into like a global power setting mode. And so you can customize that yourself by setting up a struct and passing it to our power library, or you can use one of our pre-optimized settings. So we have audio specific optimizations. We have I2C specific optimizations. We have a development mode that turns everything on in case you're using USB or crypto or whatever. And so that's an easy way for you to take your code and by changing one line of code, try different power settings. We have our data ingesting libraries. So how you ingest the data from audio or I2C, how you take that and compute features on it and so on. Remember that in-place compute that I was talking about? We're creating that library in terms of trying to make it as in place as possible. There's some things you can't do, but we try. And so we've done all that work. You don't have to do it. We have some power measurement tools. So you can label regions of interest. You can output those regions of interest using GPIO to your joule scope, and then you can use those signals to zero in on those, like the inference part versus the feature extraction, so you know what you're optimizing. You can also use a RPC, remote procedure call functionality, to control a script that maybe controls your joule scope and so on. And then finally, we have a long list of examples. So the neuralSPOT itself has some basic examples on how to do this stuff and how it's instrumented for power optimization. But our Model Zoo, which is kind of a sister offering from Ambiq, it's a series of um, it's a series of example models that are based on neuralSPOT, and they will take advantage of the same things. All right, and then we have one special entry in the Model Zoo, which is not TensorFlow Lite micro based. So you can look at that to see how you would implement some of these models in straight C. And this is my last slide. This is basically just a cut and paste from, and I deleted some stuff that wasn't relevant, from some of our code. So here's how you would actually go about maybe instrumenting your code, right? So if you're in energy measurement mode, you want to turn off JLink, the ITM interface, the SWO interface. You want to use a UART, which is lower power, and it doesn't need the crypto enabled. So you turn on your UART, you initialize a power monitor state. That's the thing that will tell the joule scope of the external device what monitor mode you're in. And then you set the NS power set monitor. Oh, shoot. Oh, that's a cut and paste error. There's a set power config is what that should say. And you pass it in NS audio optimal, which is an optimized set of configuration parameters for our power environment. So the proper call is NS power config. If you're not doing that and you're still developing your code and you want all the printfs to work and everything to work, you just set the NS development default. It's fairly optimal, but we're not turning off critical peripherals. And then you would go about and you say set power monitor state, AI data collection. That will tell joule scope, hey, set these signals so that you know you're in the data collection phase as you label that. You use our ring buffer kind of IPC to collect that audio data so you're doing more in place computation. You might set the monitor state to, okay, now we're going to do feature extraction, and then you call our library for Mel spectrogram computation. You pass it in this buffer, and that will, again, try to compute in place where it can. And then finally, you tell joule scope, hey, I'm inferring now. And maybe around, so the invoke is what actually calls the infer, right? Maybe you want to set high power mode in that region. So you turn it on, invoke TensorFlow Lite for microcontrollers and inference, and go back to low power. So that's the kind of things that we can do. This is a toy example. Clearly, I made some cut and paste errors, but this is how it actually looks in the neuralSPOT example. All right. I know that was a kind of dense, but we got through it in about 30 minutes, which is great. Thank you all for attending and sticking with it. My name is Carlos Morales, and thanks for being here.